Hi everyone, we're continuing with finding PFDs, partial fraction decompositions for rational expressions. Now before, we dealt with the easiest case when the denominator could be factored as a product of distinct linear factors. Here, we have repeated linear factors, or powers of a linear factor. The cube of x plus 2, basically 3 copies of x plus 2 multiplied together. So this case will be a bit more complicated, and the form will be a bit trickier. That's why it's very important to know how to write down the correct PFD form. If you don't know the form, you're dead. First off, I want to know if this rational expression is proper. Is it bottom heavy by degree? Well, what is the degree of the numerator? The degree of the numerator is 2. Now, look at the denominator. If you were to expand this, if you work out the cube, what would be the leading term? You don't have to write out the other terms. Just ask yourself, what would be the leading term if you were to cube x plus 2? The leading term would be x cubed, and then you would have lower order terms. But bottom line, what degree is the bottom, the denominator? That degree is going to be 3. So this will be proper. It will be bottom heavy by degree. So remember, when you see something like this, imagine expanding this out, but you only have to really worry about the leading term. You don't have to write out or worry about the lower order terms. So imagine that these are written out in descending powers before determining the degrees. Again, we're happy that this is proper because it means we do not have to do what? We don't have to do long division. As much as long division is fun, we love long division, we don't have to do it here. Sorry. Step 2, let's factor the denominator over the reals, but fortunately, it's already been done for you. The cube of x plus 2, that's already factored. Now, bear in mind, I have the right to give you a problem where I have this expanded out, x cubed, yada, 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 and then it's your job to factor it back to the cube of x plus 2. That's fair, okay? You'll have to remember chapter 2, right? Maybe the rational zero test and synthetic division to get the factorization, but that would be fair to go backwards from here to here. But in this example, I'm being nice. I'm giving you the factored form of the denominator. You're welcome. Step 3, determine the required PFD form. Now, this is going to get a lot of people in trouble, but you have to know what the PFD form is if you have any chance of getting this problem correct. How do we deal with repeated linear factors? Remember, the key idea is that with the denominators, you do what? With the denominators, you run up to the power. Here, you're going to run up to this cube. Now, of course, since you've done the homework, 7.4 number 1, I'll give you 10 seconds to write down the form. You got it? All right, repeated linear factors, we run up to the power. Remember, A, B, and C represent real numbers that are unknown at this point. We run up to the power. A over x plus 2, all to the first basically, plus B over the square of x plus 2, plus C over the cube of x plus 2. That's what I mean by running up to the power. If we had a fourth power down there, we'd have another fraction with the fourth power down there. Now, if you wish, or if your friend wishes, your friend could have written the PFD form basically in reverse. So maybe your friend puts the cube down here, keeps the square here, puts the first power guy or first degree guy down here, over here. That's okay. There are various ways to write the PFD form. Maybe your friend likes to decrease the power. That's fine. So there are different ways of writing the PFD form, but you basically have to have something like this, where you have unknown real constants on the top and the first, second, and third powers of x plus 2 on the bottom. And you can reorder these fractions. That's fine. Now, it turns out that there is only one ordered triple, a real value for A, a real value for B, and a real value for C that will make the right side equivalent to the left side. Remember, all of these are simpler than this. This had x squared over the cube of x plus 2. Even this guy has just a number over the cube of x plus 2. And these will be easier to integrate in calculus 2. Incidentally, as long as this thing is bottom heavy, it does not matter what this polynomial is. It could be 1, it could be 7, it could be 3x minus 5, it could be x squared plus 4x minus 2, whatever. As long as it's bottom heavy, if you have any non-zero polynomial on top, here's the breakdown. Here's the PFD form. Okay, step 4. We need to obtain the basic equation. In order to accomplish that, we multiply both sides, basically every term on both sides, by the LCD, which is always going to be the denominator on the left-hand side. We multiply by the LCD, this denominator over here on the left. Now, hopefully you can do this mentally, but if you wish, you can, of course, write out the cube of x plus 2, the cube of x plus 2, the cube of x plus 2, and the cube of x plus 2, and see how things cancel out. That takes a fair bit of writing, but if that really helps you out, then go ahead and do it. But we hope we can do it mentally, right? If we multiply a fraction by its own bottom, we get the top, x squared, equals. Again, we're multiplying all these fractions by the cube of x plus 2, right? It might help if I kind of move this guy around, kind of like a ghost. Well, I'll do this. All right. So we multiply this first fraction by the cube of x plus 2. We have 3 copies of x plus 2 over here, 1 copy of x plus 2 over here. What happens? A pair of x plus 2's cancel, but you still have 2 survivors up here with the a. So we have a times the square of x plus 2. The third factor here gets canceled by this guy. What if we multiply the second fraction by the cube of x plus 2? Well, 2 pairs cancel out. 2 pairs divide out to 1. We have 1 copy of x plus 2 left, and that attaches to the b. So plus b times 1 copy of x plus 2. Plus, what happens if we multiply the third fraction by the cube of x plus 2? Well, here, just like with the left side, this cube of x plus 2 completely cancels out with the bottom over here, completely cancels out the bottom here, and we're left with c alone. All right, plus c. So that's going to be our basic equation. Remember, you must write the basic equation as part of your work. Now we're going to use the basic equation to find the values we need for a, b, and c. So remember the strategy we used last time in method 1. Do you see at least one real value for x we could use that will zero out some of these terms? Look at this. What value for x would really help us here? I think -2. Ironically, -2 was the one number outside the domains of these guys, but actually that's the number we want to plug in. Remember, the basic equation holds true for all real values of x, including the exclusions from the domains up here. In fact, those exclusions are the guys we want to plug in. So let's plug in x equals -2. Okay, we plug it into both sides, the left side and the right side. Again, here's the basic equation. We plug in -2 on the left. Now, folks, when I plug in -2 on the left, do I get this? Oh, -2 squared. Be careful. For once, we really need these grouping symbols. Whenever you perform a substitution, be prepared to put grouping symbols, especially when you have these negative signs involved. So we want the square of negative 2, which is what? That's going to be positive 4 on the left side. Over here, what's going to happen when we plug in negative 2? Well, basically, we got a 0 term here, right? Plug in negative 2, we get a 0 term there. Look at this. I mean, you don't have to show all this work. Basically, tell me you're going to plug in x equals negative 2, and I'll believe you. C equals 4, right here. C equals 4. In fact, if you say x equals negative 2 and write down c equals 4, I'll believe you. Okay, I hope you're careful with this mentally. Again, the square of negative 2 is positive 4. These are zeros, 0 terms. C over here. C equals 4. All right. Now, assuming we haven't made any mistakes, C is 4. If we haven't made any mistakes yet, and we haven't, then C will be 4. So you know what? We can go ahead and plug that in. We can update the basic equation. And that's actually a really good idea because it helps remind you that we know what C is. We know C is 4. So let's run with it, right? Let's run with it. Because if you forget that we know the value of C, then you might end up doing a lot more work than you have to. We know C is 4, so let's use it. Let's plug him in. He's no longer unknown. Okay, at this point, we can either stick with method 1, the plug-in method, or we could switch to method 2, matching coefficients. But let's save that for later. As some of you might prefer method 2 here when you learn it, but let's stick with method 1 for now. Method 1 can still be okay. In principle, both methods work for all of these problems. All right, we already plugged in x equals negative 2. We'll just use your numerical sense, right? Look at these things. What are some other nice values of x to plug in? And there are no wrong answers. You could, in principle, be weird and plug in pi, although I wouldn't recommend that. Or your SSN, I wouldn't recommend that for all sorts of reasons. But what would be some nice values of x to plug in to make this simpler? Okay, let's try plugging in values. I think x equals 0 would work out. For one thing, we know 0 squared is 0, all right? I think 0 would be a popular choice. All right, so let's plug in x equals 0. We get 0 squared, or 0, on the left side. You don't have to show this work here. I mean, if you show me the next step, 0 squared is 0, okay? 0 plus 2 is 2. 2 squared is 4. That's 4 times a, plus 0 plus 2 is 2. So we have 2b over here, plus the 4. We could clean this up. We can divide both sides by 2 and switch sides. So the zero's on the right. Divide this by 2, we get 2a plus b plus 2 equals 0. And then it might look more natural to us if we subtract 2 from both sides and we have our non-zero constant on the right side. You don't have to do that, but I think we're more familiar with this form. 2a plus b equals negative 2. A nice linear equation in a and b. Okay, that's nice, but what's a and what's b? We're going to need another equation. So we're going to have to plug in a third value of x. Remember, we plugged in x equals negative 2. We plugged in x equals 0. Can you see another value of x that would work out nicely? Many of you might say 1, and that would work out fine, but you know what's even nicer? How about negative 1? Because that'll make these guys really nice, although you have to be careful over here. If you're not careful with signs and parentheses, maybe positive 1 is better. But if you're like me and you'd rather have easy arithmetic, negative 1 actually works out nicer. Okay, so let's plug in x equals negative 1. On the left side, be careful, it's the square of, put the negative 1 in parentheses because you're going to end up with positive 1 on the left side. The square of negative 1 is positive 1. Over here, okay, basically negative 1 plus 2, that's 2 minus 1, or 1, right? The base here is 1. Same with this guy over here. It's 1. Okay. Well, 1 squared is 1. We have 1a, or just a, over here, plus 1b, or just b, plus the 4. Let's subtract 4 from both sides. We get negative 3 equals a plus b. Switch sides, and we get a second linear equation in a and b. Now we know from before that c equals 4. We got that from before. And now we have these two linear equations in two unknowns, A and B. Guess what? We have what S word? We have a system. And that's, again, a key reason why this stuff is in chapter 7. Actually, author Ron Larson used to have this partial fraction stuff back in chapter 2 because he thought, well, if we're talking about rational expressions in chapter 2, that's a good time to bring up this stuff. But then he realized in one of his later editions of his pre-calculus book, wait a minute, they have to know how to solve systems. So maybe chapter 7 is better. Anyway, you solve this system. It shouldn't be too hard. You could use substitution or the addition method. Multiply this bottom guy by -1 on both sides and then add. Basically subtract equations, right? And you end up with A equals 1 and B equals -4. Try to show the work if possible. This system is not too bad. You can use the methods from early in chapter 7. So remember, C was 4. We already got that from before. And we now have values for A and B. A equals 1, B equals -4. Remember, C was 4. Are we done? Are we done? Not quite. We have to plug these values in. This was the PFD form. Plug in 1 for A, -4 for B, and 4 for C. 1 over x plus 2 plus -4 over the square of x plus 2 plus 4 over the cube of x plus 2. And I would accept that. Although, if your number up here is negative, it is conventional to factor or pop out a -1 factor. So we would normally write this as 1 over x plus 2 minus +4 over the square of x plus 2 plus 4 over the cube of x plus 2. Either is fine, as far as I'm concerned. If your friend wants to write these in reverse order, that's fine. This fraction minus this fraction plus this fraction, that's perfectly okay. You can rewrite these fractions in a different order as long as the appropriate signs are attached to the fractions. And again, if you want, you could check this. A check is optional, either by building these fractions up, getting a common denominator, and then you should get this back. Or it might be easier just to take a blank piece of paper, scratch paper, and just rework the problem from scratch and make sure you haven't made any mechanical errors. On an exam, I'm normally pretty lenient as far as mechanical errors go, but I really hope you get the right PFD form and that you show me that you know what you're doing, that you know appropriate methods. But if you make a small arithmetic error, I tend to be fairly lenient because I don't really expect people to check. It feels good when you see this in a check, but I don't expect people to check. So far, I've talked about method 1 for finding A, B, and C, using a plug-in or substitution method, finding nice values of x to plug in, and maybe solving systems. In method 2, we're going to discuss the matching coefficients method, and the harder that denominator gets, the more complicated that factorization in the denominator gets, the more complicated a form you get, and then the more you want to shift from method 1 to method 2. You can always use a hybrid, and both methods will work entirely in all these problems. But later on, in our next example, we're going to start mixing the methods, and we're going to look at the matching coefficients method. Okay, next time.